Welcome to our demo for our new SIMD softcore at FPL by Imperial College London. You can find all our source code at philippos.info/Simodense. After this introductory slide, there is a short video demonstration. For this demo, we will use our softcore called Simodense for developing and evaluating an example SIMD instruction. As shown in the figure, Simodense has a RISC-V core with a data and instruction caches at level 1 and a shared last level cache that accesses the entire address space. Our test platform is Ultra96, which also has 4 R cores running Linux. Our goal in this demo is to develop a simple SIMD instruction for the softcore. Our selected task is to add two 256-bit vectors of 8 integers each, as shown in the figure. This is also equivalent to the add kernel of the stream benchmark that calls the same instruction repeatedly until a list of sums is produced for bigger problem sizes. In order to implement and call this instruction, we use the I' instruction type that allows simultaneous accesses to 2 vector registers as source and 2 vector registers as destinations and 2 base registers. As we only use 2 sources and 1 destination, the vector register destination 2 is aliased with 0 when calling an assembly. Also aliased with 0 are the other unused operands here for our example use case. For the opcode, we use the predefined custom instruction 3 opcode as shown on the top right corner. On the bottom, we show how these can be called from inline assembly in C or C++ programs. First, we calculate the immediate field that contains the register names. In this example, VRS1 is 1, VRS2 is 2, VRD1 is 3, and the other destination register is aliased with 0. Then we call this value to call the custom instruction C3 with minimal modification to the GCC toolchain. In this slide, we can see the steps that I will be showing in this demo for implementing and evaluating new SIMD instructions. This demo only demonstrates simulation, but further information for FPGA implementation is provided in the source code repository. First, we modify the provided Verilog template to implement vector addition. Then we compile the RISC-V binary for the softcore to execute, and then we validate that our instruction works in simulation. First, we download the GitHub repository locally. Then we find the custom.v file that has the empty template for the new instruction. This module will be the placeholder for our vector addition instruction. Starting from the top of the interface, we have a single valid bit for all the inputs. Then we have destination register names and the source register data. Then we have the output valid bit, which will depend on the pipeline latency, the delayed destination register names, and the output data for the destination registers. Then all this logic here is responsible for appropriately delaying the registered destination names according to the pipeline latency, which is defined by this constant here. As our addition only takes 1 cycle, we change this to 1. Then we place our source code here, which just updates the data for the destination register 1. We also make a small change for the destination data to correspond to a register. Then we write our C program to test our instruction. Note that this file exists as part of the benchmarks folder. As you can see, it is relatively simple. First, it prepares 2 lists of random numbers. Then it measures the start time in order to measure the time for the vector-based function. And then it finalizes the measurement for this function. Then there is the equivalent logic in serial code. Then it prints some more statistics, such as the speedup, and finally it compares the 2 results as a validation step. With respect to the addList function, it just iterates over the list by an increment of 8, representing 8 32-bit integers for a 256-bit vector. First, it loads the 2 vectors into vector registers 1 and 2. Then it calls the new instruction, and finally it saves the results to proceed with the next iteration. We can now compile this file, and as we can see, we also get the start address, which can be used by the softcore to find the first instruction to be executed. We then copy the firmware to the simulation folder, and we update the start address to the correct one. Now we can run our simulation. As a conclusion, our instruction works correctly as all additions match between the vector and the serial version. We can also find the speedup, which is reported to be 8.96 times. Thank you very much for your attention. You can visit our paper presentation at FPL for more information on the framework. You can also visit our repository for implementation details on FPGAs. as well as for more advanced vector instructions with pipeline implementations.